All right, good people. Sorry about that. Here we go. The last video. We're going to do examples 4 and 5. We'll leave example 6 for in class. I'll ask you to do number 6 and maybe bring it to class to to discuss. Example 4. We are given the graph of f prime. Discuss the concavity of the original function f and determine if f has any points of inflection. Okie dokie. So remember that concavity is related to the second derivative. But I don't have the second derivative, I have the first derivative. However, I know that the slopes of the first derivative, the slopes of f prime, lead to the second derivative, right? The derivative of the derivative will give me the second derivative. So where is the slope equal to 0 on this graph? So I'm going to use a different color. The slope is equal to 0 here. And I'm going to say that is 1/2. So if I were to draw a sign chart, I love my sign charts, I would say that at 1/2, the second derivative is equal to 0 because that's the slope of the slope function, the derivative function. On the right side, all my slopes are positive, right? I'm not talking about the y values, some other negative, some positive. I'm just saying the slopes are all positive. So therefore, the second derivative is positive. And then on the other side, my slopes are all negative, leading to that green 0 slope. So these are all negative. That means that the original function f is concave down and then it's concave up. So we can say f is concave down on the interval for x's that are less than 1/2 because f prime is decreasing, which means f double prime is negative. That's an arrow. And I can say that f is concave up on x's that are greater than 1/2 because f prime is increasing, meaning the second derivative of f is positive. Okay, so reread those statements, see if they make sense. And because the second derivative changes signs, we can say f has a point of inflection at x equals 1/2. And the reason is because the second derivative changes signs. And it changes signs at x equals 1/2. So let's make sure we show where it changed signs. And really, maybe that's what we should have written up here as well, right? H has a relative maximum at x equals 6.3 because h prime changes from positive to negative at x equals 6.3. Same thing here. H changes from negative to positive at x equals 0 and x equals 7. But example 4 shows us that we can analyze the concavity of a function given the first derivative graph by looking at the slopes of the first derivative in order to determine concavity and points of inflection. As we go to the last example here, thank goodness, we're given the graph of g prime. Use the graph to determine intervals of concavity and determine if g has any points of inflection. So same idea, there is a 0 slope here, and there's a 0 slope here. So that looks like it's going to happen. Oh, where does this happen? Why don't we just call it 2, and why don't we just call it -1, just for simple sake here. So again, if you want to get organized, you can do it without it, but if you want to get organized, we can say that the second derivative is equal to 0 at -1, and 2. Why do I know that? Because the slope of the derivative graph is 0 at those places. And then all the slopes before that are all positive. All the slopes in between -1 and 2, they're all negative. And all the slopes after x equals 2 are all positive. That means the original function g is concave up, concave down, then concave up. So g is concave down on the interval from -1 to 2, -1 less than x less than 2. Because, how do we know this? G prime is decreasing, which means the second derivative is negative. I also know that g is concave up on intervals for x's that are less than -1 or x's that are greater than 2, because g prime is increasing. So the first derivative is positive. I'm sorry, the second derivative is positive. And then finally, g has 2 points of inflection at x equals -1 and at x equals 2, because g double prime changes signs at those points. And just like that, again, we're analyzing the graph we can't see. We're analyzing the graph of g, the original function, by looking at the graph of g prime and using the graph of g prime to extract second derivative values which describe the concavity of the original function. I'm going to pause here. If you would, attempt number 6, see if you can figure out. Number 6 puts everything together, right? Can you find where the original graph is increasing and decreasing, as well as relative extrema? Can you find out where the original function is concave up or concave down, and any points of inflection? And this is all from a derivative graph. Try to do that, bring it to class, and we'll discuss that out.